Today I'll be talking about accelerated motion in physics. First thing you have to know is what equations you want to use. Everything up here goes with accelerated motion. These two specifically go together. If there's no acceleration, you use just distance equals rate times time. Okay, so we have a first example. A car traveling at 15 meters per second accelerates 20 meters per second over a time of 1.25 seconds. Find the average acceleration. That's a pretty easy equation because acceleration is just velocity over time. So for part A, acceleration, or A bar, you could say A average as well, equals delta V over delta T. Delta V is just our final minus initial. So our final velocity is 20 meters per second minus 15 meters per second over. Our final time is 1.25 seconds. And our initial time was 0. So we divide. 20 minus 15 is 5. Divided by 1.25 seconds, meters per second, which gives us 4 meters per second squared. So that is our average acceleration. Alright, so for part B, we're finding how far did it travel in this period of time. So what we can use is this equation. Whenever we're given or we find an average acceleration, this is the equation we're probably going to be using. Or if we're not given a time, we can also use that equation, which was final velocity squared equals initial velocity squared plus 2 acceleration average delta t, or delta d. And we plug in what we're given. We know final velocity is 20. 20 squared is 400. Equals 225 plus 2. Acceleration is 4. Delta d is what we're solving for, the change in distance. So we can subtract 225 on both sides. That gives us 175 equals 8 delta d. So our change in distance is just 175 divided by 8. So delta d, divide 8 on both sides, and we get about 21.8 meters. Okay, next example. A tennis ball drops from a height of 20 meters. How long does it take to drop? So we have some tennis ball drop into the ground 20 meters high. We just want to figure out how long it takes to get there, and then how fast is it going when it hits the ground. Whenever you're dealing with acceleration from gravity, because that's what we're using here, we know gravity equals negative 9.8 meters per second squared. We're going to be using that equation. That's probably the most important equation in this entire section. So gravity is negative 9.8. We know we're just dropping the tennis ball, so the initial velocity is 0, because we didn't give it any motion before we just dropped it and let gravity take it. So initial velocity is 0. Initial height is 20, so we can say our S naught, that's our distance, is 20. Distance initial. That's pretty much all we have right now. We also know our final distance. Distance final, S, or SF, is here when it hits the ground. So that's 0 for us. So we just plug those into the first equation. That'll help us solve part A. So we have 0 equals, just plugging it into that first equation up there. 1/2. Acceleration is negative 9.8. T squared plus velocity initial is 0 times t plus s naught is 20. So that's gone. Don't need that. So we solve this. Subtract 20 minus 20. So we have negative 20 equals negative 4.9 t squared. Divide by negative 4.9. So this becomes t squared equals negative 20 divided by negative 4.9 is the same as 20 divided by 4.9. Then you just take the square root of both sides. So t equals square root of 20 divided by 4.9. So our time is about 2 seconds. So that's the answer for part A. 2 seconds. So for part B, what speed is it going when it hits the ground? We can use the second equation. Remember, those two go together. So part B, we have final velocity, which is what we're looking for, equals acceleration times time is 2. 2 seconds. We don't need that. So our final velocity, we use the 2 seconds because we know how long it took to drop that 20 meters. It took about 2 seconds. So 2 times 9.8 is 19.6, and it's negative because it's falling towards the ground. So we get a negative. Number 3. A ball is launched from the ground at an angle of 30 degrees at 30 meters per second. When will it reach the peak of its motion? Alright, so let's list our givens. They give us a vector because it has an angle and a magnitude. So we have a vector. (30 meters per second at 30 degrees. Remember, this is r and theta. But we can't do anything with the vector. We need it in x and y components. So that's the first thing we're going to want to do, is convert it to x and y components. So let's get a visual first. So it's launched from the ground. (30 meters per second, 30 degrees. We want an x and a y for that. So here is our Vy. Here is our Vx. We have 2 nifty equations. We know Vx is r cosine theta, and Vy is r sine theta. So Vx is 30 cosine 30 degrees, and this one is 30 sine 30 degrees. Anyways, so our Vx is 26 meters per second. And our Vy is 15 meters per second. when will it reach the peak of its motion? So if we think about a graph, we want to know when it hits the peak of its motion. We're thinking the velocity in the y direction. When you throw something, at the top of its motion, the velocity is 0. Alright, so Vy equals 0 up here. Not down here when you just launched it. So we can use our second equation. We know this is 0. Well, we equals a times t plus v naught. So we'll just plug it in. So 0 equals, a is negative 9.8, t is what we're finding, and our initial velocity in the y direction, because these have to be in the same direction, initial velocity in the y direction is 15. So we solve this equation, and minus 15 and then divide by negative 9.8. T is going to be about 1.5 seconds.